Today's discussion is going to be about exponential functions, and typically exponential functions are written in this form. We have some y equals a times b to the x power, and in this case a and b are both going to be constants, so regular numbers. X is going to be a variable, so that's the thing that changes from time to time. B in this case will be greater than 0, and B will not equal 1 because we know that 1 to any power is just going to be 1. So what we're going to do is we're going to graph this function y equals 2 to the x, and this is an exponential because it's really in the form of 1 times 2 to the x. So there's my a term. My b term is 2, and my variable's x. And then we're going to find the domain and range. So typically on these guys, I like to take and just set up a chart of x's and y's, and I keep my numbers small so I don't have to calculate things that are too big. And I'll usually go the numbers between 2 and -2. So if I plug 2 into the x, I get 2 squared, which is equal to 4, 2 to the first, which is equal to 2, 2 to the 0, and we found out a couple of days ago that anything to the 0 power is 1, 2 to the -1 power. We know that if I have a negative exponent, I take its reciprocal and make the exponent positive, so that's a half, and 2 to the -2. Again, I take the reciprocal, make the exponent positive, so I have 1 over 4. Let's take and graph these. Here's 1, 0, 1, 2, 2, 4, -1 1/2, -2 1/4, somewhere around here. So you'll see that this graph does something like this. And that's going to be the standard look of an exponential function. It's a curve shape, and it tends to rise very quickly and then level out. You'll notice that this is leveling out at 0 because you can't take a power of any positive number and ever get a negative number. So in this case, my domain, this will go forever in the right direction and forever in the left direction, is all reals. Then my range, that's my y values. You'll notice it goes up forever, but only goes as low as 0, but never gets there. Because 2 to any power will never equal 0. So it's y is greater than 0, but it doesn't equal 0. Let's do another one. This one's going to be a little more complicated. So we have 1/4 raised to the x power, and that's equal to, or minus, and that's -5 is equal to y. I'm going to again use those same values to plug in. Two, 1, 0, -1, -2. I have 1/4 squared minus 5, which is 1/16 minus 5, which is -4 and 15/16. Then I have, plugging in a 1, 1/4, the first minus 5 is 1/4 minus 5, which is -5 and -4, sorry, and 3/4. 1/4 is 0 power minus 5 is 1 minus 5, which is -4. 1/4 -1 minus 5 is the same as, take the reciprocal, so 4 the first minus 5, which is -1, and 1/4 raised to the -2 minus 5 is equal to, take the reciprocal, exponent's positive, minus 5, that's 16 minus 5, which is 9. So, I go over 2, and I go, in this case, up to 9. And then I go, oops, 2 and up to 9, sorry. I go over 1 and down -1. I go to 0 and down to -4. I go to 1 and 4 3/4. And over to 2 and -4 and 15/16. So you'll see that my picture is very similar, except instead of rising, it drops. And if I talk about a domain, again, goes to the left forever, goes to the right forever, so that's all reals. In fact, for every exponential, the domain is going to be all reals. The range is the only thing that'll change. And in this case, the range, it appears to be leveling out at this point right here. So y is going to be greater than, and that value is -5. So let's talk about this increasing and decreasing type of graph. If a exponential function increases, like so, we said say this is a growth function. So in other words, b is going to be greater than 1, a is going to be greater than 0, and we talk about the domain being all reals, and its end behavior as x increases, y is going to increase, and as x decreases, y is going to approach, in this case, 0. If this function drops, we say it's a decaying function, and typically in this case, the b value, or the base, will be a fraction between 0 and 1. So let's take a look at a chart of some values and note the difference in the patterns of output values. So from value to value in this case, I notice I have a difference of 2 in each case. But in this exponential, while I have 2 in common, it's a multiple. And that in itself is the big difference between linear functions and exponential, this being linear because it makes a line, this being exponential because it makes an exponential, is that linear functions have constant differences between output values, and the exponential functions have constant multiples between output values. So here's a word problem. The value of Royce Company computer equipment is decreasing by the following function. So this equation describes the computer equipment's value. X is the number of years that have gone by since the equipment was purchased. We want to know the value after 5 years. So basically all they're really asking you to do is set x equal to 5, plug in and solve. So in this case I have 4,000 times 0.87 to the 5th power. And we can just pop that in a calculator. Let's go ahead and do that. And we'll have the following. I take 4,000 times 0.87, close parentheses, raised to the, here's the power button, 5th power. And this gets me 1993 point, bring that back, 68. So this seems right because it's dropping. You'll notice this b value is a fraction between 0 and 1, so this is a decay problem. And it should drop. Now, sometimes we have exponential equations where I don't have the same base. In our last lesson, we used a technique of getting the same base in order to solve exponentials, but there's no way I get a base of 3 equal to a base of 2. So we'd have to use a calculator to actually solve this problem. So let's go ahead and do that. And the way we're going to use this calculator is we're going to take and graph the two exponential functions. So my first exponential function, y1, is going to be 3 raised to the x power. In my second exponential function, I have 2 raised to the, this whole power has got to be in parentheses, so 2x power. And then I'm going to take and subtract from that 1. So now I'll take and graph this in the standard window. So I go zoom 6, which graphs it in the standard window. There's my first function, and there's my second function. And if I want to find out where those two functions are equal, I'm going to take and find the intersection of the graph. So to do that, I hit my second button, followed by my trace button, which is really the calculate button, and I find the intersection of the two. So this is the number 5. And it says first curve, I just hit enter. Second curve, hit enter again because I only have 2 curves graphed. And once again, it gives me this guess thing, which I really don't care about. So I'm going to hit enter for a third time. And what it'll do is it'll find the exact place the two intersect. So it turns out that these two equations are equal when x equals 1. So that is the value for x where the two functions will equal. And that's all we've got. I'd like you to write your lesson summary, solve these equations, and we'll talk about this more tomorrow.